Let's talk about intercepts. Now, when we studied in the two-dimensional plane and we were calculating the intercepts of a graph, we did this kind of thing. Suppose we have y equals 1/2 x minus 1. Here's its graph. To find the x and y intercepts, we just let x and y take on the value 0 and then solve for the other letter. That is, when we want the x-intercept is the place where the graph crosses the x-axis, and the y-coordinate of that point would be 0, so we let y take on the value 0, and then we solve for x. And here we multiply through by 2, and then isolate the x to find x equals 2. Now, the x-intercept we say is equal to 2. The coordinates of the x-intercept would be 2, 0. For the y-intercept, it's a similar idea. The y-intercept, the place where the graph crosses the y-axis, the coordinates of that point have the characteristic that the x component is 0. So we let x take on the value 0 and then solve for y. We find y to be -1, and the coordinates of the point would be 0, -1. All right, so that's the idea, and those concepts hold true when we go to the three-dimensional coordinate system. Now, suppose we have this equation, and this is the form of the equation of a plane. And we would like to find the intercepts of this plane with our three axes. And to do that, it's relatively simple. Once we understand this concept, it's really easy because the x-intercept is found by letting y and z take on the value 0. So we just use our equation and let y and z become 0 and then solve for x. We would have 3x equals 12, so x is 4. Now, it's important to realize that the coordinates of this point, remember, the coordinates would be an ordered triplet, and the x component would be 4, and the other components would be 0. So we have the point 4, 0, 0 as the coordinates of this point. All right, and for the y-intercept, it's a similar idea. We just take this equation. For the y-intercept now, we let x and z become 0. So those go out, and we have 2y equals 12, so y is equal to 6. And the coordinates for that point would be 0 for x, the y is 6, and the z is 0. Okay, and now for the z-intercept, same idea. For the z-intercept, let x and y become 0. They go out, 4z is equal to 12, so z is equal to 3, and the coordinates would be 0, 0, 3. Now, let's plot these intercepts on our 3D coordinate system. Let's see, we have the point 4, 0, 0. Let's see, 4 for x means we come out this way to 4. We have the point 0, 6, 0. Let's see, 0 for x, 6 for y. About right here, let's say. And then z is 3. Now, what we can do with that, these are points that are on a plane. These are just the intercepts of a plane. So we can illustrate the plane by sort of making a triangle here and just shading the triangle. And the illustration of this is a lot better in your textbook. So you might have a look at that. But it's a notion that this is part of a plane. And the plane intersects the three axes at the points given. Okay, so that's the idea. Now, the general form of the equation of a plane is this. And this is the form of the equation that we had just a moment ago for that plane that intersected the x, y, z axes. Okay, a, b, c, and d are simply real numbers here. Now, it's possible for planes, planes can intersect all three of the axes as we saw earlier, but a plane may intersect only one axis or just two of the axes. Let me show you illustrations of those two. And once again, these illustrations are in your textbook, and I strongly suggest that you look at those as well as these. Maybe those alone would be just fine. But for one intercept, imagine now if a plane is to have just one intercept, then that plane is going to have to be parallel to the other two planes. That is, if we have a plane that has an intersection point here on the x-axis, then this plane has to be parallel with the YZ plane You see, so this is a plane that now on the x-axis we're coming out this way, but we come away from that YZ plane and we're parallel with it. So that's what we're trying to illustrate here with this idea. And notice the depth perception given by these dotted segments and so forth. And over here, this is an intersection point. We have an intercept of the y-axis, but no intercepts for the other two. That means that the plane being described here is parallel to the XZ plane. So here's the XZ plane, and this plane that intersects the y-axis but not the other two is parallel with this. So that's what's being illustrated. Now, intercepts, we could have two intercepts. We could intersect two of the axes and not the third. And oh, by the way, now I didn't give the third situation over here. There are actually three situations where we have one intercept. I showed an illustration of an x-intercept and not a YZ, a y-intercept but not a x and z, and there is such a thing as a z-intercept but not an x and y. Again, look at it in your textbook. All right, let's look at a situation where we have two intercepts. Now, if you have two intercepts, it turns out that the characteristic of the plane having just two intercepts is that that plane has to be parallel with the third axis. That is, if we have an intersection point here on the x-axis and another on the y-axis, but no intersection point on the z-axis, then this entire plane has to be parallel with that z-axis, you see, for it never to intersect. And so that's what's being illustrated here, that we have. Now notice the diagram, it kind of goes across this way, but it kind of goes straight up. If the z-axis goes straight up, this plane goes straight up. You see, and it's away from that z-axis. So that's the idea. Now, if I want to try to draw a two-intercept situation involving the x-axis and the z-axis, then here's how you start. Now, I may get jammed up here because I'm not real good at this, but it's something that if you practice a little bit, then you can draw some rather extraordinary figures. But what you do is you just connect these two. All right, and now what you're trying to do is draw some kind of flat surface, and I'm drawing a flat surface. Gee, if we're intersecting the z and the x axes, then we're not going through the y-axis, and we are parallel with the y-axis. And here's how you illustrate that, is from these points, you draw a segment which goes in the direction of the y-axis, so out this way. And then down here, you want to go out this way, and you want to go that same distance. You see, so I'm trying to go the same distance that I have up there. And then just kind of connect these. And now and this is the plane that's being shaded. And now to sort of complete the diagram, you do something like that. All right, and something like this. Now you're dropping this down back here to be parallel with the z-axis. And you do a similar thing from here that is parallel with the x-axis. So it's something like that. So it kind of looks like it's a slanted situation like this, but parallel to the y-axis. Okay. Now let's talk about some rather extraordinary figures called quadric surfaces. They have some incredible names. Look at these names: elliptic cone, elliptic paraboloid, hyperbolic paraboloid, ellipsoid, hyperbolic, that should be bolic with a C, my bad, hyperbolic, oh no, it's a hyperboloid of one sheet and a hyperboloid of two sheets. The diagrams for these are in your textbook. I'm not even going to take a shot at drawing them. We want to look, though, at the associated equations of them. And it just looks like a lot of hieroglyphics at this point, I'm sure. But there are some characteristics. Once you look at it a little bit, stare at these equations just a little bit, some of the characteristics of ellipses and hyperbolas that you studied before kind of emerge. They kind of come through the fog. And also you notice certain things like this, that in this equation, for example, you have x squared and y squared, but z is to the first degree. And the comparison between these two is that you have a plus sign between these two fractions and a minus sign between these two fractions. That's interesting because when you studied in pre-algebra, you studied the conics in pre-algebra, you had a similar kind of equation for the ellipse. And look at this. This is an elliptic paraboloid. Right, and when the sign changed to minus between the two fractions, you had a hyperbola. Well, here we have a hyperbolic paraboloid. You see, and you might look at some characteristics of the graph that's in your textbook. Now, I do want to mention that the graphs, the illustrations in your textbook, are just one version of all of these figures. That if they are aligned along one axis, that remember, if we swap the role of x's, y's, and z's here, mix them up a little bit, then that illustration would be along a different axis. So that's just one form of several that the graphs can take. And also I'll mention to you that remember when you studied the ellipses and hyperbolas particularly, that you began your study with the orientation at the origin. That is, the center of the ellipse was at the origin. The center of the hyperbola was at the origin. The center of the circle was even at the origin. And then you moved away from the origin and the equations changed and all that kind of stuff. But here, the center sort of the universe of these figures is at the origin, you see. So they become a little more complicated if you move away from the origin. But at any rate, we have some characteristics that hold true to what we have had before, and we have comparisons that we can make among these different equations. And then we can look at some problems involving these equations. And a lot of times the equations are given to you in a rather jumbled up form. For example, suppose we want to identify the kind of figure that this equation represents. Well, at first glance you have no clue. But then you start to realize, all right, we have a variable squared here, a variable squared here, but we have one of the variables to the first degree. And we also have a 0 over here. So there's no floating constant in this problem. All right, so let's go over here and look to see if we can find an equation that has that characteristic. Now, some of these have fractions in them, many of them, most of them. All of them have fractions involved in them, but that's not a big deal. You know that A, B, and C are just real numbers. And A, B, and C could all be ones, and therefore the fractions would tend to disappear. But we have a situation right here with the elliptic paraboloid where we have a variable on one side, and it's to the first degree, and we have a couple of variables on the other side, and they are both squared, and we have a plus sign between them. You see, so if we have an isolated letter over here, and then the other terms on the other side. Well, let's go over here and let's write this in that form. We would have x equals then y squared plus z squared. And we notice that there's a plus sign between these two, and that's the characteristic of this elliptic paraboloid. So this is the equation corresponding with an elliptic paraboloid. Now, if we want to, from this point, we can answer a number of other questions without even drawing the diagram for it. Now, I believe the illustration for this is in your textbook, and you really ought to have a look at it to kind of get a good feeling for this. But we can answer questions like, what is the xy trace? Now, the xy trace, remember this idea of trace from the last section, is the sort of the intersection of this graph with the xy plane. And the intersection of this with the xy plane, every point in the xy plane has the characteristic that the z coordinate is 0. The z component of the coordinates of every point on the xy plane would be 0. And so you use that information to find the xy trace. So the xy trace is found by letting z take on the value 0, and so the xy trace is simply x equals y squared. Oh, this is a rather elementary quadratic model, you see, and so the graph of this is going to be a parabola, and so you can kind of imagine that, gee, Well, we could overanalyze this many different ways, but x is equal to y squared, and we could think about the axis upon which it is based, and then we have two values of y for one value of x. So move along the x coordinate, and then you have two values of y emanating from every one of those points. So that's kind of the idea. So you can, by the way, I should make this trace instead of track. Okay, so that's the idea. Now, take a look at this one. It's a little more complicated than the one before, but here's what I want to point out. We have an x squared, a y squared, and a z squared. That's the first thing. We have plus signs all around in between all of these. All right, that's another thing. We have kind of a floating constant out here. Okay, now, can we manipulate this into one of these forms? Certainly we can, but let's see which ones might be a candidate. You see, these two we throw out immediately because we have a first degree variable in these two. Right? And here we would throw this one out because we have a minus sign between a couple of terms, or preceding one of the terms. This one might be a pretty good candidate. Wow, that's maybe a real good candidate. Hey, wait a second, this is it. We've got, we're adding all of these guys, and we have a constant on the right, and the constant is 1. Well, we can create that situation over here rather easily. You see, we can just kick that 4 to the right side. We can add 4 on both sides, and we can make that 4 become a 1 by dividing through by 4. We need to do that anyway in order to cause this coefficient to be a 1, which is the form over here for our equations. So let's divide through by 4. We would have x squared over 4. When we divide this by 4, we get y squared over understood 1. And I'm going to emphasize the fraction idea with this. And then plus a z squared over 4. And remember, we added 4 to put it on the right side. When we divide by 4, it becomes 1. So now we have exactly the form that appears in this equation, and this is the equation corresponding with an ellipsoid. So that's the equation of an ellipsoid.